Hello. It's a little late, so we're doing an alternative version today. We just watch a video and go to bed.
Mechanical pendula that are connected by a string with a constant tension. Which means that if you make a deviation in one pendula, it will create a force on the neighboring one. Now, take one end of the series and twist it by 360 degrees. This defect we have just created is called topological soliton. If the series of pendula is infinitely long, it is maximally stable and it behaves like a solid object.
Lines across the universe.
It is well localized and it can move like a particle. You can also scatter it with other solitons and it would behave as if you were scattering two solid balls. But what is really staggering to me that this object we have just created obeys the laws of special relativity. It has a maximum speed of propagation and it undergoes the length contraction that is given by the relativistic gamma factor. You can also create a bound state, like a molecule, with anti-soliton, which oscillate with a certain frequency. But when this system moves, the frequency decreases, which represents the time dilation. Again,
It's some trippy shit. Wow.
according to the gamma factor. Yet, anti-soliton, which oscillate with a certain frequency. But when this system moves, the frequency decreases, which represents the time dilation. Again, according to the gamma factor. Yet we didn't use any complicated physics, just a simple pendula and a springs. So where does the relativity come from? In 1938, two physicists, Yakov Frenkel and Tatiana Kontorova, studied crystals. But crystals in nature are not perfect.
Another thing I'm working on is my posture. So my current lack of an extra screen is good posture practice.
Contain dislocations, which put a strain on the crystal lattice. Frenkel and Kontorova wanted to study the structure and dynamics of the lattice near these dislocations. That's a very difficult task to do when you consider the whole crystal as a bulk. And therefore, they introduced a simplified one-dimensional model where you have a chain of atoms or molecules. The atoms are bound, meaning if you make a deviation in one, it will create a force on the neighboring ones. This lattice is then subjected to a dimensional model where you study the structure and dynamics of the lattice near these dislocations. That's a very difficult task to do when you consider the whole crystal as a bulk. And therefore, they introduced a simplified one-dimensional model where you have a chain of atoms or molecules. The atoms are bound, meaning if you make a deviation in one, it will create a force on the neighboring ones. This lattice is then subjected to a periodic sinusoidal potential, which represents the effect of the whole crystal on the chain. In this potential, all the particles want to go to the minima, and this creates a nonlinear interaction between the potential and the interparticle interaction. But as long as there is the same number of particles as the number of minima, then the lattice is pure. It has a minimum energy configuration when all the particles are at the potential minima, which we call trivial configuration, and it can vibrate, creating waves, which we call phonons. But the moment you add another particle into the lattice, then you create a dislocation, since you have more particles than the number of minima. It can create a stable dislocation, as you can see here, or unstable dislocation, which can move across the lattice. This dislocation is often called a kink. And now the minimum energy configuration is not trivial. Despite the simplicity, this model was very successful in describing wide variety of physical phenomena, like dislocations in the crystal, charge density waves, phase transitions, and even surface physics. The interesting things start to happen when you consider the so-called continuum limit of this model, where the number of particles goes to infinity, so it creates continuum. It's quite reasonable thing to do, because in a real crystal, the lattice might contain like 10 to the 20 atoms. And from our point of view, it seems like a continuum. But you have to be careful when you do this limit, because both the number of particles and also the number of minima goes to infinity. But you have to somehow keep track on how many extra particles you have in your model, because this tells you how many kinks you have inserted into the system. So the result is an equation, and this is how it looks like. It's called a Sine-Gordon equation due to its similarity with a very famous Klein-Gordon equation. This equation, the Sine-Gordon equation, completely describes the behavior of the lattice. It is a differential equation, and the result of a differential equation is a function which serves as a map. You put a number into it, and it gives you a different number. For example, if you take this differential equation, which tells you that the second derivative of a function you are looking for plus the function itself is 0, then you can immediately spot one possible solution, sine of x. If you take a second derivative of sine of x, you get minus sine of x, and plugging that in will satisfy the equation. But differential equations don't have just one solution, but many. For example, a cosine would do fine as well, or any arbitrary linear combination of the two. This equation was easy, but in the case of Sine-Gordon, the things are more complicated. It is a partial differential equation, which means that the function we are looking for takes two values as an input, which is the position and time, which gives you a certain value. Moreover, there is this term which is nonlinear in phi, which is the function we are looking for. And would you guess what is the worst equation you can get to solve? Yeah, it's a nonlinear partial differential equation. Finding a function that would satisfy this equation can be very hard, and most of the time it's actually impossible, and you can only solve it by numerical integration using computer. But to understand what the solution really means, it can be sometimes quite difficult. For example, a kink solution would look like this, whereas anti-kink solution would look like this. You can see that both asymptotic ends of the function are in different vacua, and it is the reason why it's maximally stable. You can imagine this configuration in Frenkel-Kontorova model in such a way that here all the particles to the left are in the potential minima. Then, at the location of the kink, there is a shift by 2 pi, since there is one extra particle. And all the particles to the right are also at the potential minima, but shifted. We say that this configuration has a topological charge of +1. For anti-kink, the situation is different in such a way that instead of one extra particle, you are missing one particle, which makes the shift in the opposite way, and therefore the topological charge is -1. If you have kink-anti-kink configuration, then the topological charge is 0, as you have the same number of particles as the number of minima, but the energy of the configuration is high. But in 1969, Albert Scott did a major leap into intuition behind the Sine-Gordon model, where he took the series of coupled pendula and made a continuum limit. The equation he got is again Sine-Gordon equation. One of the interesting things that you can immediately notice about this equation is that it treats spatial and time coordinates identically, which you would expect from a relativistic equation. But this equation was actually discovered much earlier in the history. Already in 1870, Alfred Enneper found the same equation in his work on differential geometry and found a soliton solution. A bit later, in 1882, a Swedish mathematician, Albert Bakund, found a way how to get from one known solution another unknown solution, using Bakund transformations. Later, this equation proved to be using Bakund transformation.
I was really hoping I wouldn't need geometry for anything. But I was wrong.
Later, this equation proved to be completely integrable, which means that you can always find the function that completely describes the system. And what is also interesting is that this is the only nonlinear partial differential equation that is also relativistic and fully integrable at the same time. You can have a simple waves, which we call phonons. They are not very well localized in space, as you can see on their energy densities, which is all over the place. This solution basically represents how heat and sound spread in the material. You can also imagine it to be a quanta of sound, if you will, and they travel at the speed of sound. So you can say that they are effectively massless. But this solution only holds for a small deviation of the pendula, where you take only the linear approximation of the Sine-Gordon model. Then you can have a kink solution. This behaves more like a particle. It is localized in a small area. It has an effective mass and moves always slower than the speed of sound. As you can see, the closer to the speed of sound it moves, the more contracted it is, according to Lorentz contraction. You can also see the same thing when you look at its energy densities. For a static kink, its mass is a number 8, in the units where we put all constants to 1. But if it moves, its effective mass increases by the gamma factor, as in special relativity. Since it's a topological defect, it's maximally stable and cannot be destroyed. When you scatter the kink with another kink, they will just elastically bounce off of each other. But you can also have an anti-kink solution, which basically means that you twist the series of pendula in the opposite way. And when you scatter it with a kink, then they basically annihilate for a moment. But since the energy is still there, a new pair of kink-anti-kink is being created. In this model, when you scatter the kink and anti-kink together, they will always create a new pair. But in more complicated models with a different potential, it can happen that they will decay into a bunch of phonons and completely annihilate. The reason they can annihilate is because if you have a kink and anti-kink, you can see that they together are no longer protected by their topology. The only thing that keeps them stable in Sine-Gordon model is their energy and the integrability of the system, which means that this collision cannot produce phonons that would carry their energy away. The kink and anti-kink can form a bound state, which we call breather, and each breather is represented by a certain frequency omega. This configuration basically means that the kink and anti-kink pair have not enough energy to escape to infinity. It is basically a soliton molecule, but the interesting thing is that you can think of breather as a clock. And if you make this configuration move, the frequency of the breather decreases according to relativistic time dilation. It is very fun playing with this stuff. And the interesting thing is that you can think of breather as a clock. And if you make this configuration move, the frequency of the breather decreases according to relativistic time dilation. It is very fun playing with this stuff. Yeah, it takes some time to write the code, but the intuition you gain with playing with these models is actually priceless. But yeah, if you wanted to write a code for everything, you wouldn't learn much because that would take just so much time. But you don't have to, because my sponsor Brilliant has already done it for you. They offer thousands of interactive lessons from math, data, programming and AI, and you learn by your hands. And it's my link to the video. We have a theory, so thank you Brilliant for sponsoring me, and now back to the video. So by a simple chain of pendula, we have achieved quite a lot. We have a theory of massless phonons and a massive solitons that behave like particles, and they can form a bound states, and all of it satisfies the special theory of relativity. And you can be quite philosophical about this. So dialect, if you are watching, maybe this is your ether. Some sort of particles coupled together where phonons are photons and these kinks are particles that undergo length contraction. Because this basically provides a length contraction mechanism, and you don't have to postulate it as in Lorentz ether theory. But there is much more you can do with these models. You can find a duality between this model and a high energy QCD, where you have free quarks as kinks. Then the color symmetry can be represented by a topological charge, which tells you how many times the solution is twisted around. For example, kink have a topological charge of 1, whereas anti-kink has a -1. And for example, for breather, it has a 0, as there is no twist. QCD for high energies has also unbroken chiral symmetry, which in our model can be represented by invariance under the shift by 2 pi, since we have a sinusoidal potential. Then you can attribute each solution to a specific quark state. You see that U and D quark are the same, but just shifted. It is because we have a chiral symmetry, then these two are basically identical particles. But you have to forget about electric charges, because quantum chromodynamic doesn't deal with electric charges, but just color charges. Now if you want a quantum chromodynamics for low energies, where you have confinement and different masses, then you have to somehow break the chiral symmetry. To do that, you just lift one of the vacua in the Sine-Gordon potential. This is called double Sine-Gordon model, and it is no longer fully integrable. But you can still find a baryon or meson solutions. For example, this is a baryon of U and D quarks. And this is a meson solution for U anti-D. You can also scatter these configurations together, and the results would be quite non-trivial, because you no longer have a nice function that would describe the complete behavior of the system. And I know that baryons should have 3 quarks to form a bound state. But we are only limited to 1 dimension, and therefore we have only 1 color. But one could play with these models for higher dimensions, and I believe that it would be a lot of fun. And big thanks to all of you who support me on Patreon. I really appreciate your help with these videos. And also thank all of you for watching.
Wow. Wow.
Thank you.